Hello everyone, my name is Aurélien Bellet. I'm a researcher at INRIA in France. I'm going to present some joint work with César Zabater and Yann Ramon on differentially private distributed averaging. All right, so this is a workshop on federated learning. So the goal in federated learning is to learn models from data that is owned by several participants. And we want to tackle two challenges in federated learning. The first one is how to provide differential privacy guarantees to the participants so that they don't reveal too much information about their data in the process. And the second challenge is how to ensure the correctness of the computation when there are potentially some malicious users taking part into the protocol that might try to bias essentially the outcome to their advantage. So in this context, our focus is on the problem of distributed averaging, which is a key building block in many federated algorithms. So we have a set U of n users or parties. Each user U holds a private value. So here I'm going to assume for simplicity that it is a real value in the 0-1 interval. And then the goal is to accurately estimate the average of the private values without revealing them. Okay, motivation comes from the fact that many federated optimization algorithms that are used right now, so this includes federated averaging, but also very recently introduced federated optimization algorithms, they can all be written in this sort of very general structure. So there is a set of rounds, and at each round, essentially a user will use the current global model to compute a local update based on its local data and send this update to the server. And then the server will essentially compute the average of these updates and then send back this average to the users. Okay, so we can see that in these algorithms, this distributed averaging is essentially the key interaction that arises between the users and the server. So of course, there is a lot of related work on differentially private distributed averaging. One classic baseline, of course, is local differential privacy, where users will essentially perturb their input locally before sharing it with the server. So unfortunately, this leads to poor utility. So there is a very big gap with what can be achieved in the trusted curator setting, where the users will send their clean input, and then this curator would compute the average and only add noise at the end. The good thing about local DP is that it is often communication efficient and has also some robustness to malicious users, at least in some protocols, because each user only sends very little information, like sometimes as small as a bit. So it is hard to make a big inference on the result. Recently, there has been a lot of work towards trying to a little bit bridge this gap between local DP and the trusted curator setting. So a classic approach is to combine differential privacy with secure aggregation techniques from crypto. So if you do this, you essentially recover the trusted curator utility, but you have to pay a cost that is essentially a number of order n messages per user. So each user has to essentially exchange messages with all other users in the network, which is not at all scalable for when you have many users. Okay. It is possible to enforce correctness in these protocols, for example, using things like verifiable secret sharing. This comes at usually at an additional cost. And I want to quickly mention here that there is some recent concurrent and independent work on breaking this order n barrier in secure aggregation. I won't have time to talk about that now, but I suspect one of these papers will be also presented at the workshop. So I think this will make for interesting discussions. Finally, there is a lot of recent interest in this shuffle model of differential privacy, where essentially users randomize their input locally, like in local DP, but then these inputs are passed to a mixnet or a secure shuffler that will mix these messages before sending it to the server, so the server cannot tie each message to a user. So it's been shown that you can recover in this model the trusted curator utility. But okay, it's not clear. At this point, people have studied this mostly from the maybe theoretical perspective. So in terms of practical implementations, it's not so clear what can be done and how efficient that can be. And I'm not also aware of work that essentially tries to tackle this robustness issue, so how to enforce correctness or prevent malicious users to bias the outcome. Okay, so our key contributions are to introduce a new protocol, which is, as you will see, quite simple and efficient. And the main idea is essentially to have users perturb their input locally, but also to exchange correlated Gaussian noise with other users along the edge of a network graph. And this network graph can be quite sparse. And in particular, we show that we can recover trusted curator utility with only logarithmic number of messages per party. So this is unlike classic secure aggregation, for instance. And we further show that we can guarantee the correctness of the computation by using cryptographic primitives like homomorphic commitments and zero knowledge proofs. All right, so let's first look at the protocol. You see it's very simple at this point, and it doesn't resort to any crypto technique. So the parameters of the scheme are a graph, like I said, because the users will exchange along the edges of this graph, where nodes are users, and two types of variance. So there is a variance sigma delta and a variance sigma eta. Okay. So the protocol goes as follows. Essentially, each neighboring users will exchange some noise, so jointly draw some noise, x here, from which has variance this sigma delta. And this is going to be some pairwise canceling noise. So essentially, each one user will add it, and one user will subtract it. Okay. Then each user will also generate some independent Gaussian noise. Okay, this in blue here, this eta mu, which has variance sigma eta. And then each user will reveal essentially the sum of its private value, the sum of the pairwise noise that it has generated, and also add the independent noise term. Okay, and it reveals that, it makes that public. And so what will happen, essentially, you can see quite easily that we can get an unbiased estimate of the average from this by just averaging these noisy values that have been revealed by each user, and essentially the pairwise noise will cancel out, and we will be left with a variance which has the same, which is depends only on the variance of the independent noise. Okay, and so this pairwise noise will not affect the utility, but it will help achieving stronger differential privacy guarantees by hiding more the individual values. Okay, so what can we say about the privacy? So first of all, we have to define an adversary. So what we consider here is a proportion row of colluding malicious users, okay, in the network. And these users, they essentially observe all communications that they take part in. So the only things that are unknown to them is the private values of other users, which are honest but curious, and the pairwise noise that pairs of honest but curious users have exchanged. Okay, everything else is known to the adversary. We will denote by UH the set of honest but curious parties, so those who are not malicious, and by GH the subgraph induced by the set of honest parties. So our guarantees will depend very much on properties of this graph. And what we can show first is that GOPA can achieve epsilon delta differential privacy for any epsilon delta bigger than 0, as long as the graph of honest user GH is connected, and as long as the variances of the two types of noises are large enough. Okay, so this is not surprising, but we make a much more strong statement. Precisely, we show that the variance of the independent noise, the one that will not cancel, can be as small as in the trusted curator setting. So essentially, we can recover the utility of the trusted curator setting. And at the same time, we show that the required pairwise variance, which will cancel, will depend on the topology of GH, of the graph of honest users. And essentially, it will depend on it through properties of spanning trees that are embedded in this graph. And essentially, the better the spanning tree, so the more branching factor it has, the smaller can this pairwise noise be. Okay, so these are more like general statements, and then we can instantiate them for different types of graphs. And so here I'm going to focus on the most practical results, which consider the case of a random k-out graph. Okay, so in this case, the graph G is obtained by letting all users randomly choose k other users in the network, and then they become their neighbors. Okay, so here we're going to assume that k is of order log n. Okay, so only need to exchange noise with a logarithmic number of other users. And it also depends on rho, of course, the proportion of malicious users, because, okay, the more malicious users, the larger k needs to be, so that we can guarantee with high probability that the GH will be sufficiently connected. We're going to set the independent noise here to be essentially exactly equal to what we would use in the trusted curator setting using the Gaussian mechanism. Okay, so then the utility essentially is exactly the same as in this trusted curator setting. And the pairwise noise here is essentially proportional to the independent noise times the number of honest users divided by k. Okay, then if we do that, we can show that GOPA indeed is epsilon delta differentially private. So the same guarantee as in the trusted curator setting, up to a small constant in the delta, which is proportional to epsilon prime that you would get in the trusted curator setting. Okay, so essentially we get trusted curator utility with logarithmic number of messages per user, which is nice. And I want to insist here, so that I want to make clear that I have stated this result here with big O notations for clarity, but we do track constants, and so our theoretical results they give practical values for k and sigma delta that are sufficient to achieve the guarantees that we want, and those are very practical in practice. So you can see examples in the paper, and we exactly know also quantify the small degradation in the delta compared to the delta prime. Okay, so these results can really be leveraged in practice. And we can even obtain even smaller values for k and sigma delta by numerical simulation. So again, please see the paper for that. I want to talk briefly about correctness. This will have to remain a bit high level because, okay, there are quite a lot of technicalities. So first, what is the goal? So the privacy guarantees that I shown before, they do not depend on the behavior of malicious users, so they would stand whatever their behavior is. But of course, the utility of the protocol will depend on what malicious users do. And if they tamper with the protocol by, for instance, sending incorrect values, then they can bias the outcome. Okay. And this is made even easier by the fact that okay, each user is supposed to draw some independent Gaussian noise, so a malicious user could still pretend that it has been honest. It just was unlucky in drawing this Gaussian random number. Okay, so we want to avoid that. Of course, it is impossible to force a user to give the right input to the algorithm, and I want to emphasize that this also holds in the trusted curator setting. So there is not much we can do about that. What we can make sure is that essentially what we want is enable each user to be able to prove the following properties. The first one is that the input is in the right range. The second one is that all pairwise noise are canceling. The third one is that the independent noise terms are indeed drawn from the prescribed Gaussian distribution. And the last one, that the revealed value is the sum of the private value, the pairwise noise terms, and the independent noise term. Okay. So how do we do that? So we're going to rely on here on crypto primitives. So we're going to have users publish an encrypted log of the computation. And for this, we use per-cent commitments. So these commitments, they allow essentially users to commit to a particular value and without revealing them. And this value cannot be changed later. It can potentially be revealed, or one can prove properties about it without revealing it. Okay, and these commitments are additively homomorphic, which makes it easy to prove some properties that are additive. But we need to go beyond that, as I've shown before, for the properties that we need to prove. So we also construct a little bit more elaborate zero-knowledge proofs to be able to prove that the correct computation was done correctly. Okay. So there are a lot of technical subtleties here that I don't have time to mention. So for instance, we have to work in fixed precision and so on. So I'm not going to go into that. And of course, the details are in the paper, but I can state a little bit of informal results to give a flavor of what we can guarantee. So essentially, we can show that under the discrete logarithm assumption, the DLA, which is a classic computational assumption in crypto, a user U that passes the verification procedure will essentially prove that the revealed value was computed correctly. And additionally, by doing so, you will not reveal any additional information about its private value. And this is true even if DLA does not hold. Okay. So DLA is really to ensure the soundness of the proof, but is not required to guarantee the privacy, which is nice. The cost per user remain linear in the number of neighbors, so things remain efficient, at least to this extent. Okay, there are additional costs, of course, but things remain rather efficient. We can prove consistency across multiple runs using also those zero knowledge proofs. So when you do multiple runs or the same data or similar data, like one does in iterative algorithm for federated learning, for instance. And we can handle also user dropout to some extent. So again, I don't have a lot of time to talk about that, but the details are in the paper. So thank you for your attention, and you can check the paper on arXiv. Thanks a lot.